title of this video is Coated Nanoparticle with Crawlers. The main goal of this video is to explain the concept of multiscaling in computer simulation in soft matter. We have chosen a system composed by 4 different types of molecules. First, we have the biggest molecule, that is a colloidal particle, in fact, moving across the solvent bath. So we have also polymers covering the colloidal particle and crawlers. These crawlers are molecules of intermediate size that hinders the colloidal motion. So what we have here is the Brownian motion of the colloidal particle, but this diffusion is affected by the presence of the crawlers. The crawlers create a cage around the colloidal particle. In addition, we have the motion of the grafted linear polymers, which expels the crawlers, so it's kind of a shell that covers the colloidal molecule. Then we have also the bombardment of the solid molecules. It can be water or any other liquid. So we have different time and length scales involved in this problem. First, the characteristic diffusive time, that is the time that employs the colloidal particle in moving half its diameter. Then we have the characteristic seam relaxation time of the tethered polymers, and we also have the diffusive time of the crawlers, which is of course shorter than the colloidal relaxation time. And another time scale that is relevant in the problem is the solvent particle, which defines the Brownian motion. And it is clear that we also have different length scales. The particle, the colloidal particle, I mean, is of the order of hundreds of nanometers, and for example, in this case we have chosen 50 nanometers, and the size of the crawler is 5 nanometers. The size of the polymers is of the order of some nanometers as well. So we have the radius of gyration and the size of the molecules, that is of the order of 1 or 2 nanometers. This multiscaling is important because this is observed in several systems in soft matter. So we have a bunch of time scales in one problem, as we can see here. So the idea is how to couple all these dynamics to explain a particular phenomenon, in this case the diffusion of a colloidal particle. So this colloidal particle is affected by a characteristic diffusing time. The effect of the caging of the crawlers is also relevant, and the radius of gyration of the linear polymers that defines the size of the shell. So this kind of a core corona particle that has a certain hard core component and a shell that is formed by the polymers. So we can observe different time and length scales of this problem. So the main idea is how to include all these time and length scales in this problem. And how to connect the different time and length scales involved. So how the gauging of the Crowders modifies the diffusion coefficient of the colloidal particle, and how relaxation time of the covering formed by the shell affects the size of the cage formed by the Crowders. So as you can see, there are lots of time and length scales involved in one simple problem, even though we have employed a coarse grain model and not an atomistic model, which is of course more expensive in terms of computation. So our outlook is that the multiscaling is a very interesting problem in soft matter, because you can have different time scales as well as different length scales in one simple phenomenon, in this case the diffusion of a colloidal particle.